So good morning. Welcome to the second class of natural language processing. And from this class onwards, we will teach the mathematical modeling behind NLP technology. So for this week, we start from the simplest modeling technique, namely the foundations of probabilistic modeling. This class corresponds to chapter 2 of the textbook. The title is Counting Relative Frequency. As you can guess, all of the models we see for this week work by counting relative frequency. So this class will consist of, so in the first part, I will show you or give you a review of probabilistic modeling techniques. And then the second part, we will talk about language models, in particular, n-gram language models. For the third part of this class, we will move on to naive Bayes text classification. It's a kind of probabilistic text classification model. So first of all, let's look at what is modeling here. By the mathematical definition, when you build a model, you make an aspect of a real-world problem by simplifying it to the extent that exact mathematical computation is possible. In other words, we talk about model all the time when we talk about NLP. But what is a model? A model is a mathematical simplification of natural language processing, where you abstract away a lot of things that are too complicated that hinder your mathematical computation. Okay? And you simplify the problem to the extent that you can formulate your task by using a neat mathematical form. So this is modeling. So as we learn mathematics and physics, we already seen a lot of modeling examples. For instance, right, when you throw a stone off a cliff, right? Throw the stone off the cliff. There are a lot of things you need to worry about. So, like what kind of stone it is, like wind, the shape of the stone, etc. But it turns out that if you consider all of these things, the problem is complicated. And a lot of factors are relatively trivial, right? When you try to measure when the stone will fall to the ground. Okay? So there are a few things that matter. The gravity, right? How high the cliff is, etc. While other things like the wind, shape of the stone are relatively less important. So you make a mathematical abstraction by treating the stone, right, as a mass point, so that only a few factors matter. So similarly, when you build an NLP model, you follow similar principles. And here in this chapter, we talk about probabilistic model. And what is the probabilistic model? The modeling target is a probability. So you build a model to calculate the probability of something. Of course, this something is related to languages. So what is a probability? In the philosophical sense, it tells you the chance of something happening. What is the probability you're having a final exam this term? What is the chance in the long run? Well, in the empirical sense, it tells you the relative frequency of something happening. So if you have taken 100 courses and 60 of them have final exam, then you have a guess. Okay? Given any class, okay? you have 60 out of 100 chance that you have a final exam. Okay? So this is the empirical sense. In the end, you draw a connection between the empirical sense and the philosophical sense of probabilities, but that is the target of your models. In other words, your models will calculate the probability for something. In terms of the language, there are a lot of things which you can calculate probabilities for. For example, I speak a sentence, and you can calculate the probability of a sentence out of all possible sentences. Right? Obviously, the probability of me saying hello is more than the probability of me saying build a hyperbolic model. Okay, so that is relative frequency. You say hello more often than you say something more mathematical. Right. Given that, I want to give you a very simple example of a probabilistic model. And this example doesn't cover language, but it's so simple that it can serve to illustrate some fundamental principles. So for example, let's consider tossing a coin, okay? Tossing a coin. You want to know whether the coin lands facing up or down, okay? Head or tail. So you know, exact calculation of this result is very difficult because it depends on the coin itself, how you hold the coin, the friction, the table, the distance to the table, right, and initial spin, etc. So many different factors. So this is a good chance, a good situation where probabilistic models can help. Okay, and when you build a model, one very important thing is you need to parameterize the model. What do I mean by parameterization? Okay. Well, this is an important term. We will encounter throughout the term. Okay. It means that it defines a model parameter, okay, through which your modeling target, okay, for this week, the probability of something is computable. So you define a function, f. And f takes an input and calculates the probability of an output. So, but inside f, if there are some model parameters, then it is called parameterization. You define this function as model parameter. So for coin tossing, this problem, we want to make it very simple. No input, okay? The only parameter is the probability of the coin facing up, okay? So we call this parameter theta, okay? Theta. So that's your model, okay? The whole function f equals to theta. Every time you throw the coin, you use your only model parameter theta to estimate the probability of heads. Okay. So if theta is 0.5, you bet this is a fair chance, a fair coin. Okay. If theta is 0.6, then you bet more on the head. So this is the model. Now, after you parameterize the model, what do you do next? Okay. You know the parameter is theta, but you don't know what's the value of theta. So you want to do some experiments to verify the value. Okay. So you take the coin and you start tossing it. Maybe you toss it 100 times. Okay. And you calculate how many times it ends up facing up. Right. So this is relative frequency. As I said, if it faces up 60 times, then you have 60 out of 100 as your theta. Okay. Given that, we can formulate a machine learning problem. You have a model with parameter theta, and you have a set of training data, okay? We call it y1, y2 until yn. So this n can be 100 if you toss it 100 times, but it can also be another number, right? Okay, and you maximize something in order to estimate theta. So what is this something? Okay. I said, well, you tossed it 100 times, you counted the number of heads, but there's an underlying principle, which is called the maximum likelihood principle. Maximum likelihood estimation, MLE. What does that say? It says you have a set of training data, and according to your model, okay, you can calculate the probability of your training set. So this probability is called the theta likelihood. Okay, the probability of your training data is called the theta likelihood according to your model. So this probability will be calculated by using your model parameter. And the maximum likelihood principle says, when I try to find a model, okay, I find one that maximizes the probability of my training data. Okay, so this is an optimization problem. Why is that so? We will see more reasons in chapter 5. But for now, you can intuitively understand it as what happens makes sense. You see some data, and this data comes out of reason. Okay? When you see this data, you assume that this data is likely to happen. Okay? So this is intuition, right? So when you don't know the result, you don't have any knowledge. But when you observe something, you assume that this something that you observe is very likely to happen. Okay? By maximizing the likelihood of what you see, you can find the model parameter value. So this is the maximum likelihood estimation principle. Now, let's just roll up our sleeves and calculate it. Okay? The probability of the data set. As I said, out of n tosses, maybe you say k times to find the point spacing up. Okay? Now, you can guess the probability of your data set. Here, you need to make an assumption, which is that every training instance, every toss, is probabilistically independent of each other, and they're identically distributed. What do I mean by identically distributed? It means that the underlying probability is the same. It's your model, okay? The probability is your model theta. This is identically distributed. What is independent? It means that the result of a previous toss is not dependent on the result of a succeeding toss. Okay, every toss is independent. Okay, so identically distributed dependent tosses. This is called IID. IID. Okay, if you assume that every time you toss it, the probability is IID, then the probability of your data set is the product of the probability of each instance. Okay. This is a conclusion from probability theory. Okay? So now if n times, okay, and k times you have hits, so the total probability of your data set are the total probability of all the heads, namely theta to the power of k. So you have k theta. Okay. What about the rest? Those are tails. The probability of tails, according to your model, is 1 minus theta, right? You have n minus k times seeing these data instances, so the total probability is 1 minus theta to the power of n minus k. All right? So the whole data set consists of either ups or downs. So you put all of them together, you get the first equation. The probability of data set is theta to the power k times 1 minus theta to the power n minus k. This is cool. And what do? You want to maximize the thing. in order to find the value of theta, right? So this is a optimization problem. By this optimization problem, we can maximize also the log, which is easier to calculate. Okay. The log of this thing equals to k times log theta plus n minus k times log 1 minus theta. This thing, right? So you want to find the optimal point of this equation, and we can set its derivative to 0. Derivative with respect to what? Of course, you only have one parameter. So you calculate the derivative of this thing with respect to theta is equal to this one is 1 over theta, right? So this one is okay. So plus 1 minus theta, but you have a minus 1 times this n minus k, right? Set it to 0. Set it to 0. And when you set that to 0, you do some simple arithmetic. Okay? So k over theta is equal to n minus k over 1 minus theta, right? And you calculate this, and you find that theta is equal to k over n. K over n. So you found a conclusion. The conclusion is a relative frequency. So that's the topic of this week. So what did we do? We built a machine learning model. We built a very simple model, a probabilistic model with only one model parameter. And we used a set of training instances with the maximum likelihood estimation principle, and we calculate the model parameter. After you got the parameter, you can use the model, right? So if theta is more than 0.5, you bet on it. If it's less, then you bet on tails. How you use the model. Now, after we know these principles, we can continue, right? So when we move to languages, okay, we can consider a simple case of drawing a random word from the vocabulary. Okay, so if you treat your newspaper, okay, as a bag of words, right? So just randomly choose a word from the newspaper. What can the word be? Okay, so this thing is not exactly tossing a coin, but it's sort of more similar to throwing casino dice. Okay. So, well, a dice has 6 different faces, right? They have 1 to 6. But the number of words is more than that. But it's sort of you can draw similarity between the two cups. So just throw a dice and you observe, okay, what's the number you get? Right? So there are 6 different possibilities, 1 to 6. So let's first consider this case. How do you build a model? Let's build a probability model. How do we parameterize the model? Let's be simple and straightforward. We just directly use 6 parameters to represent the probability of 6 numbers, 1 to 6. Okay. In the end, you realize, no, we don't need 6 parameters. Because the total probability of all the numbers is 1. So you only need to parameterize the probabilities of 1 to 5, say. And the probability of 6 is 1 minus the sum. So you have 5 parameters. And how can you estimate these parameters? You throw the dice 100 times, okay? Throw it 100 times. And you count the number of occurrence of each number from 1 to 6, okay? So you get a set of training data. Let's say that the number of occurrence of the ith number, I equals 1 to 6, is ki. Okay. Then in the end, maximum likelihood estimation tells you ki, the theta I equals to ki over n. N is the total throws. The derivation process is extremely similar to what we had on the whiteboard, so I will not repeat it, but you can do it offline to verify whether this is true. Okay? All right. So again, maximum likelihood estimation tells us you need relative frequency. All right. So now we go back to the word case. So if you draw a word from a textbook, what is the probability of each word? Of course, you know that the word must be more probable than the word hyperbole, for example, okay? Because this is a frequent word. And you also get a hint that by modeling the probability of each word as modeling casino dice, okay, you end up with a counting relative frequency. Right? You just count the number of occurrences of each word in your book, and you get the probability of the word. So this is shown in the last equation slide. Okay, the first equation tells you the vocabulary or the set of all possible words. Okay, vocabulary V equals to W1, W2, and to WV. So these are all possible words. The last equation tells you the probability of each word by maximum likelihood estimation, okay, according to a set of data Z. This data set can be a textbook, a newspaper, or can be something generally called a corpus. Okay? A corpus is a set of texts, okay, that are used to train a model. So now you have the model of drawing a word from a random text. So this probability equals to the number of times each word appears in the corpus divided by the total number of word occurrences in the corpus. Okay? All right. Cool. Now we have built a model. A first natural language processing model. Okay, it tells you the probability of every word. How many parameters are there in the model? Around the number of words in the vocabulary, right? About the vocabulary size. Because you're throwing a dice, you know, this dice has how many the number of faces is the number of vocabulary words. Okay. So after we have this model, let's go back, step back a little bit, and review some probability theory. So, all right. So first, review the model. We build a probability model. Every probability model calculates the probability of something. And when you build a model, the first thing you do is parameterization. Okay, you define a function with model parameters to calculate your probability. After you define the model, you need a set of training data to train your model. The goal of model training is to find the value of your model parameter, okay, that maximizes something. And now we've learned that this something is the probability or likelihood of your training data. The principle is called MLE. Okay. All right. So terminology-wise, the modeling target, okay, are random variables, or variables, okay, for which there's some uncertainty. They're called random variables. And the goal of a probability model is to calculate the probability of the outcome or the value of a random variable. Okay. A random variable represents some random or uncertain event. The event is raining. The event of final exam, right? The event of you winning a lottery, etc. These are uncertain events, random events. Okay, the mathematical representation of a random event is a random variable. So every event has an outcome. Okay, it rained or it didn't rain. Okay, you throw a dice, it ends up having a number 3 or a number 1, right? So these are the outcomes of events. They are represented by the values of random variables. Okay. So let's take another example, coin tossing. The random event is tossing a coin. The random variable, okay, is coin tossing. The outcome of an event is head or tail. Okay. I define two values for a random variable, 0 or 1. 0 means head, 1 means tail. So when you build a model to calculate the value of a random variable, you essentially calculate the probability of every specific value. The probability of my random variable having 1, the probability of my random variable having 0. And the parameters to calculate this function are defined by you, by the model structure. It's called the parameterization process. Next. So random variable will follow different probability distribution. What is the distribution? Okay, by distribution, you have a global view of the probability of every possible value of your random variable. Okay? So for coin tossing, there are two values, and you put them together, it forms a Bernoulli distribution. It's a shade of all possible probabilities. Okay? Why is it distribution? By distribution, I mean I distribute the probability max of 1 to all possible outcomes of your random event. I distribute this probability mass to every random variable value, okay, so that it forms a shade. So this is called a distribution. So in other words, a probability distribution is a global view of all possible outcomes of a random event for all possible values of a random variable. Coin tossing has two possible values, and they are discrete. Okay, we call it a Bernoulli distribution. Dice casting follows a multi-Bernoulli distribution or categorical distribution. Okay, when the possible values are more than 1, okay, multiple values, this is called a categorical distribution. So you can immediately learn that when you draw a random word from a vocabulary, it's also a categorical distribution because it has more than 2 values. So maximum likelihood training for both Bernoulli random variables and categorical random variables leads to relative frequency counting, okay, or the simplest way to estimate the parameter value. But for other distributions, we don't always end up with relative frequency, okay. So for more complicated cases, MLE might lead to other mathematical forms or even no closed form solutions. Okay, we will see those later in chapter 4. And okay, so next, some other relevant distribution. For example, if you have a Bernoulli random variable, okay, and you do experiments with this variable multiple times, okay, and the whole data follows some distribution. It's called binomial distribution. So if you do a Bernoulli experiment n times and you end up with a positive result k times, then how do you represent this the probability of k out of n? So this is called a binomial distribution. Similarly, if you do your categorical experiments multiple times, you end up with a multi-normal distribution to describe the probability of different types of outcomes. Right? In addition to discrete random variables, sometimes you will also have continuous random variables. So in chapter 12, when you read chapter 12, you will see something. But we won't cover chapter 12 in this term, okay, but it doesn't stop you from reading it. For a continuous random variable, it doesn't make sense to calculate the probability of it having a specific value, okay? But it makes sense to calculate the probability of the variable falling into some range, For example, you can have a uniform distribution of a continuous random variable, okay? Which means that the probability density is uniform, okay? So the probability of the random variable falling into any range only depends on the size of it. Here on the slide I show you if some random variable falls between A and B, then the whole probability of this random variable falling into this range is proportional to B minus A. Okay. Also, you have another continuous random variable, Gaussian random variable. So it falls into a bell-shaped distribution where there's one value around which the probability is the highest. Okay. And further from the value, the probability density is lower. Right. So next, in addition to one variable, sometimes you have a random vector value. So a vector is a set of multiple variables that might or might not be dependent on each other. For example, you can extend one continuous variable to a vector. So where you end up with a three-dimensional or higher dimensional space for calculating probabilities. And here in this picture, I just show you a review of a uniform random vector, a Gaussian random vector, okay, in which every dimension is independent with each other. So these will be useful for chapter 18, but again, these are not covered in the classroom teaching for this term. But if you're interested and you have some background on random vectors, it will be helpful for you to read chapter 18. Now, let's move back to this class. For this class, we're only interested in Bernoulli random variables, categorical random. You're very familiar with this. And we can start doing language modeling. So what is a language model? A language model calculates the probability of natural language sentences. Okay. For example, I showed you the probability of hello is more than the probability of building a hyperbolic model. Okay. So the modeling target is the probability of a sentence. Okay. We will see different ways to parameterize this probability, to calculate this probability. So we can parameterize the probability of a sentence by calculating the probability of words or simpler phrases. Okay, so here we need to define a technology term called n-grams. So what is an n-gram? An n-gram is n consecutive words. So a unigram is one word. Okay? Any word is a unigram. A bigram is two consecutive words. Eat pizza. Okay, drink pizza. Okay, these are all bigrams. Okay, trigrams are three consecutive words. cat, eat, mouse, mouse, eat, cat. Well, any three words together, trigram. Okay, so you know n-gram. So similarly, you can have 4 grams, 5 grams, 6 grams, 7 grams, etc. Okay. So the language models that we will discuss today are n-gram language models. Okay. So first, let's look at these language models. They make a strong independence assumption between word in a sentence. It assumes that every word is IID in a sentence. Okay. So we discussed IID earlier, right? These kind of models are bag of words models. They treat a sentence as a bag of words, okay, without any dependence between words. So by this, we can calculate the probability of sentence as the product of the probability of each word in sentence, as shown in this equation. Now the probability of a sentence is like throwing a casino dice multiple times, right? Number of words equals the number of throws. The probability of the sentence is the product of the probability of everything. And you already know how to estimate the probability of every word, right? When you have a corpus, you calculate the relative frequencies, you have the parameters, right? And now when you use these parameters in your unigram language model, whenever you just multiply the probability of every word together, you get a probability of sentence. Good. So by using a unigram language model, okay, you can already estimate the probability of hello and the probability of building a hyperbole model. Maybe in your experiments, okay, you can build a unigram language model by a corpus that either we give to you or you crawl from the internet, okay? You can build a unigram language model, and you can use the model to calculate the probability of sentences. And you can see that intuitively more frequent sentences are more probable than intuitively less frequent sentences. Okay? These are lab experiments. But you will face a problem. What's the problem? Out of vocabulary words. Okay? So, if hyper is not in your training corpus, okay, and you have one sentence hyperbole model, you have another sentence string hyperbole, okay, you will sort of know maybe hyperbole model is more probable, but your model will give 0 to both sentences because the probability of hyperbole is 0. Okay? This is for the out of vocabulary word. The relative frequency is 0. You never see that in your training corpus. How can you deal with that? Okay. So to deal with that, you need some trick, engineering trick. Okay, the trick is to have a special token called angle bracket, OOB, angle bracket, okay? So this token is used to represent all words that are unseen in training data, okay? And you define the frequency of this word to be 1, okay, rather than 0. And you get a non-zero probability for OOB word, right? They're all represented by the special token. And the token has a frequency of 1, you assume in your training data. But that's unfair. you have words that have frequency of 1 in your training data. If OOV is 1, then it's unfair to those words. How can you solve the problem? Again, you have a very simple trick. Why don't you just add 1 to the count of every word? Okay? So OOV, it has a count of 1. So those words that appear only once have a count of 2, etc., etc. Okay. So this kind of technique is called add-1 smoothing. Okay. Add-1 smoothing. You add 1 to the count of every word. So in the end, the probability of word is shown in the last equation. Right? So it's the relative frequency in the corpus plus 1. Okay. Divided by the total number of words, or including the special OOV, okay, for each of which the count is incremented, okay? So this is called add-1 smoothing. With add-1 smoothing, you can build a probabilistic language model now. In your experiment, you build the model and you type different sentences. But here I show you a figure of probability distribution, okay, segment of probability distribution with the original counts and after add-1 smoothing. And you can see after add-1 smoothing on the right, the distribution is less sharp. And that's why it's called smoothing. You make the distribution more smooth, less sharp. Okay, that's called smoothing. Smoother distribution. But if you have an eagle eye, you notice that in my slides, there's a footnote saying I didn't use add-1 smoothing, but I used add-10 smoothing. I added 10 to the count of every word, okay, to make the smoothing effect sharper. All right. So this leads to a general model called add-alpha smoothing. You have an alpha, which you can adjust. This can be 1, can be 10, can be any number. So when you have add-alpha smoothing, you add a number alpha, okay, to every word in the vocabulary and out of vocabulary word. And you smooth the language model. There are 2 things I need to mention about add-alpha smoothing. First of all, this alpha is something you can adjust. It's something that affects your model performance. It's called a hyperparameter because it's not decided during your MLE model, but it's decided before your MLE model training. It's a hyperparameter which you can adjust manually before you train your model. Okay. So, how do you adjust your hyperparameter? Okay. You can decide the value of a hyperparameter, and then you train your model, and you run your model on a set of test data. You look at the performance, and then you change the value of hyperparameter again, okay? And then you train your model, and you test your model on a set of test data. You compare the performance. You choose a better hyperparameter. This is called hyperparameter tuning, okay? How do you evaluate the performance of a language model? You won't see that today, but you will see that at chapter 6. I will tell you how to evaluate language models at chapter 6. And you don't want to directly compare your models on a set of test data, in the sense that you want to use your test data only once to estimate the real performance, okay, on unseen data. So if you don't want to leak, okay, information about your unseen data, you don't want to tune on test, tune your hyperparameter on test data. So how can you solve the problem? You can split your test data into many sets, okay? At least one set for development test, and one set for final test. Okay, the final test data can be treated as held out data. You don't touch it. Okay, you don't touch it when you tune your model hyperparameter. But the development test data, you can look at the result all the time. Okay. As a result, now you have three sets of data. Okay, one is called training data. We're already familiar with. One is called held out test data or final data. Okay, you use it very, very carefully, maybe only once after you already optimized everything for it. Because that final test data will represent unseen data. Okay, so you don't want to leak information from it. The third set of data is called development test data. Okay, you don't mind checking it from time to time. So this is about hyperparameters and how do you verify your model. Second thing about add alpha smoothing. There is some theory behind add alpha smoothing. You want to learn the theory, you should read chapter 12. Okay. All right. So if you know some probability theory for continuous random variables, and you want to learn something, some theory behind add alpha smoothing, you can read chapter 12 offline. So next, let's go on. We have seen unigram language models, and we have seen smoothing. Okay. So we want to continue to build a more sophisticated language model, or five-gram language model. So what does that do? Okay, first of all, unigram language models cannot help you disambiguate we eat pizza and we drink pizza. Because the word eat, the drinks, and pizza can all be frequent. And the frequency of eat might be larger or smaller than the probability of drink. We don't know. So, but obviously, the sentence he eats pizza should be more probable than the sentence he drinks pizza. Why is that so? The reason is that eats pizza is more possible than drinks pizza, right? So how can you parameterize your model to take this into account? Okay. This brings us to something called conditional probability. Okay. So given that the previous word is eat, what is the probability of next word being pizza? This is called a conditional probability. We're not talking about the probability of seeing pizza itself alone, right? We're talking about the probability of seeing the word pizza given that the previous word is something. Okay. And this previous word is written in the condition part of your probability. All right, this is called condition probability. And we should know that the condition probability of pizza given eat is higher than that given drink. Okay. So for those of you who almost forgot conditional probabilities, I show you something called the Venn diagram. So this gives you an illustration of the idea of conditional probability. So on the left, I show you the probability of a random variable value, okay, A. The whole rectangle represents all possible values for the probability max, okay, of the random variable. And the circle shows you the value of random variable A, okay. So the probability of A happening, okay, is the area of this circle divided by the area of this rectangle. All right. Now, if you look at the right, there's a second variable called B. Okay. Well, actually, a second event called B. The random event B happens. So when you estimate the probability of event A given event B, okay, you measure the overlapping area, the red area, okay, divided by the area of B, rather than estimating the whole area of A divided by the rectangle. Why? Because now your condition is that B happens. So everything you discuss should be under the scope of B. Okay. When you consider things under area B, the fraction of area A divided by the whole area of B is the conditional probability of A given B. All right. So this shows you in intuition what is the conditional probability and unconditional probability. Okay. So you have an exercise. So will the probability of A always be higher than the probability of A given B? Okay, that's an exercise. You can try to think about the answer by looking at the Venn diagram. Next, training diagram management. Okay. Still, we use maximum likelihood estimation to count the relative frequency. However, this time we have a condition, right? So we can't just count the relative frequency of a word out of a corpus, but we have to count every word after your condition word. In other words, if the previous word is not it, then no matter whether the current word is theta or not, you just don't count it, right? So you only count words when the previous word is it, when you calculate the probability of something conditioned on it. Right. That translates the last equation. So PW2 given W1 equals to the bigram W1, W2 frequency divided by any W, the bigram W1, W frequency, right? Of course, you can also do smoothing, etc., to avoid out of vocabulary bigrams. Okay, next. But bigrams are more sparse. The chance of having unseen bigrams is higher than the chance of seeing unseen words. And here I give you another technique for reducing sparsity called backoff. What is backoff? You're trying to estimate PW2 given W1. But if the bigram is not seen in your training set, you want to use the probability of W2, okay, itself to roughly approximate the bigram probability. But when you have W1, W2 in your training data, then you don't have to do that. Okay. So you do a linear interpolation of the conditioned probability of W2 and the unconditioned probability of W2. This is called backoff. You back off to unconditioned version by reducing the conditional dependence. And you have a hyperparameter lambda to balance the two factors. Okay? Lambda can be set to between 0 and 1. Right? When lambda is large, you assume that this bigram probability plays an important role. But when you reduce lambda, you make it more smooth by having the unigram probability playing a more important role. Okay, this is how you train the condition probability. You can do this experiment. So after you train this probability, you need to use the probabilities to calculate the probability of sentence. How do you do that? Okay. Now, let's assume that the sentence is W1 to Wn, n words, right? And to make the beginning of sentence also fall into the scope of bigram probabilities, okay, you add another special token. Right? Similar to OOV, you use angle bracket to surround it. It's called S. S is a special token to denote the beginning of a sentence. /S tells you the end of a sentence. Okay? So you add them to the beginning of the end of a sentence, and you calculate the probability of sentence by the total probability of every bigram in the sentence. PW1 condition on S, P W2 condition on W1, etc., until P slash S given Wn. Okay. Well, this is a little bit similar to unigram language model, right? The product of every word, but now it's binary. So now you should ask a question. Hey, but why do you do that? Right? How can you guarantee that this represents the probability of a sentence? Right? How can you prove to us that this is the right way of doing it? Right? Now, let me prove this to you. I use two techniques to prove this. One is called the probability chain rule. One is called the independence assumption. Let's say P, okay, as, okay, for simplicity, let's just remove this S. Let's say P, W1, W2, until Wn, okay? So, how do you calculate that? Let's say it's equal to P, W1, and P, W2, Wn, even W1. Oh, why is that true? Why is that true? Let's come back to the Venn diagram. Okay. This is A, this is B, right? So two events. Okay, this is one event, W1, this is another event, a joint event of the rest of the sentence. A and B. So you know that P, A given B is equal to this thing divided by B, right? And you also know that P, B is equal to B divided by square, right? So if you multiply this together, what do you do? What do you have? PA given B times PB is equal to this thing divided by the square. Okay? And what is this thing? This thing is the event that both A and B happen, right? So this is the joint event, both happen, right? So this is one event, this is the other, given the first one. So in general, you have P A and B is equal to PA given B times PB, right? It's also equal to PB given A times PA. So this is not formal, but Venn diagram illustration of what happens here. So when you have this, then you have this principle. You can also express W2 out, right? But this time we have a condition W1 and times PW3. Okay, right? W3 to Wn. So you can extract PW1, PW2 given W1. Now, here's the condition. The condition is W1 and W2, of course, because it's split before W2 and the rest, right? Condition on W1. We're always on W1. So now, we can continue PW3 given W1, W2 condition until PWN given W1 to Wn minus 1. So this is called the probability chain rule. We just separate out one variable after another. Okay. But by using this chain rule, we won't parameterize our model. Why? Because this is still a very, very long sequence, not good parameterization. So, you know, for mathematical modeling, we have to simplify things in order to make things computable. All right. So the way we simplify things is to remove those probability dependencies from the condition. So if you remove every condition, we end up with a unigram language model. But now if we remove, okay, something except for the last word, okay, we end up with a bayesian language. PW2 given W1, PW3 given W2, until PWN given Wn minus 1. Okay? So this step is called conditional independence assumption. Okay, this is an approximation. This is not exact, but this helps you to parameterize your model. Okay, so I prove to you. Okay, I prove to you that when I use the product of all bigram probabilities, I calculate the probability of the sentence. Right? Now, bigram language model is complete. Okay, your lab will contain this. Okay, you can write a bigram language model. So next, so whatever next will be familiar to you. So we can continue to enlarge the N, right, in n-gram language modeling, and we have a trigram language model. When we do have a trigram language model, we still have the beginning of sentence added as a special token, but this time we add two special tokens. Angle bracket S, angle bracket S to the beginning of sentence, right? So when you look at this, when essentially W1 is equal to S, right? We can remove this term. Why? Because we always assume that PS is 1. The beginning of the sentence is always S. So when you remove this one, the remaining is the bigram, right? So for triangle language model, we add 2S to the beginning of the sentence. And the remaining derivation is the probability chain rule and the independence assumption. Okay, and we end up with a model that calculates the sentence probability by the product of every trigram probability. So this is a trigram language model. Let's review it. The modeling target is the probability of sentence. The parameterization of the model is to use trigram probabilities as the only parameter type. Okay. How many parameter instances are there? Is proportional to how many trigrams are there in your corpus, okay? And also proportional to the vocabulary size to the power of 3, okay? Not all of these trigrams are seen in your training data. But the outer vocabulary ones, you use a special token to denote, okay? So you can build a trigram model now. The training is still maximum likelihood estimation, but this time you count word by the previous 2 words. And you can also do smoothing. When you do smoothing or backoff, you back off trigram probabilities by using bigram probabilities and unigram probabilities. And you introduce 2 hyperparameters to balance the linear interpolation. Okay. Here in the slide, I show lambda 1, lambda 2, lambda 3, but you can have the 3 of them summing up to 1. Okay. This is sparsity issues, and we also have more techniques with sparsity. And in particular, I think 2 of them are worth learning. One is called good Turing smoothing. The other called Nasser-Naik smoothing. And these 2 technologies are written in the textbook, and I advise you to read them, but I won't discuss them here in the class. One reason is because nowadays people use neural models. Although these advanced smoothing techniques are mathematically appealing, okay, they are no longer used in practice. So I just highly suggest that you read them for learning the thinking behind them. Okay, they'll be useful for your knowledge. Okay. Now, I give you a trick. When you do your experiments, you calculate the product of trigram probability. So when the sentence is very long, the product can be smaller and smaller. Sometimes they can challenge the bound of your numerical representation. For your computers, for floating point numbers, you have a numerical limitation, right? So to avoid this, you can use the log of probabilities to substitute the probabilities. Okay, and you can do the sum of log probabilities instead of the product of probabilities to avoid numerical overflow. Next, here I give you some examples that we had for the book. Right? So we built Shakespeare, and then we use these language models to generate the sample sentence. And as you can see, the higher the value of n is, the more the sentence like real Shakespeare writing. Okay. I guess for many people, the trigram language model, they can sample, so although they don't make sense, they sound like Shakespeare. Okay. All right, I leave it to you to read more offline. So, but now let's move on. So there are two more things for me to talk about. So one thing is generative model. When you build this language, okay, you essentially treat a sentence as a set of random variables, okay? And each random variable is a word, and you draw probability dependencies across words. So when you write the chain rule, essentially I derive the first figure, okay? Every word is dependent on all the previous words. This is a probability graph to show the generation of sentence. You generate it word by word. So when you generate every word, you condition on its previous word. Okay? So this is called a generative story. If you make independent assumptions, okay, between words, you simplify the first figure to the second figure and third figure respectively. Okay? If you use back-of-word independent assumption, you got a unigram model. Okay, when you assume that every word is dependent only on the previous word, you get a bigram model, which is the second figure. It's a chain. When you assume that every word is dependent on only the previous two words, you get a trigram language model, okay, which is the third figure. Now, these independent assumptions are named after the mathematician Markov, okay? So they're called Markov assumptions. So bigram language models make the first order Markov assumption. Trigram language models make the second order Markov assumption. And all of them are generative models, which tells you how to generate the joint probability of a set of random variables, okay? All generative models can be represented by these graphs, okay? And the nodes are random variables. Edges are conditional dependencies between random variables. And you will see more theory when you read chapter 12. But we will see a lot of other generative models throughout this term. So for today, the last thing, model called naive Bayes model. Let's just move on to that model. Okay. For naive Bayes model, the modeling target is the probability of a class label given a document. In other words, the task that we try to solve is a classification task. For example, you can classify news, okay, into sports news, political news, technology news, or financial news, okay? So you're given a piece of news text. You try to classify what category does it belong to. This is called text classification. Now the input is a document. We can call it D, okay? The output is a class label. We call it C. Now in the end, the modeling target is a conditional probability, PC given D, okay? After we learn the modeling target, we need to parameterize the model. We need to find a set of model parameters in order to calculate this probability. Can we follow? The word drawing example? We directly use PCD as the only model parameter. If we do that, we will use MLE to estimate the parameter, right? So we have a set of training data, which are manually labeled news data. We have input and output. We have a set of these called D. And we use relative frequencies. How do we do that? We just look at a condition. So every time a document D is labeled C, okay, we add 1 to P, C given D. We divide it by what? We divide it by the total number of times we see the condition or the document D in the training data. Okay, to build this model. But immediately you will find a problem. This model doesn't generalize. What do I mean? Because you can expect that every document in the data only occurs once, okay? And it only occurs once with the class label. And that's it. That's all you get when you parameterize your model like this, okay? But for all the new news data, they are out of vocabulary. You never see them. So you will not tell, okay, whether this is more likely to be sport news or more likely to be financial news. What can you do? You should parameterize the model by breaking down this thing, right? Breaking down this thing. How do you break down this thing? You will immediately observe that D can be denoted as W1, W2 until Wn. That's possible, right? And you can use probably chain rule to break it down. However, you face another problem. What is it? D is in a condition. It is not the random variable. But you can only use a probability chain rule to break a random variable, joint random event. But this time, the random event is C, the class label. D is in your condition. D already happened. You cannot simplify it. How can I solve the problem? Okay, I can use Bayes something called the Bayes rule to simplify it. Bayes rule says that PB given A is equal to PAB, the joint event divided by PA, okay? And also equals to PA given B times PB divided by PA, okay? Why is that true? Why is that true? Why is PB given A equals to PA and B divided by PA? It's here. We already wrote it, okay? You can see the reason by the Venn diagram. Okay, it directly tells you that the joint A and B probability is equal to PA given B times PB, right? So if you divide both sides by PB, and then you end up with this equation. Okay. So the last equation on the slide, okay, is called the Bayes rule. The good thing about Bayes rule is that it swaps the condition and the random variable. See, on the left-hand side, B is on the condition, but on the right-hand side, B is the random variable. So you can use the Bayes rule to swap B and C. Okay. Next, P given D is equal to PD given C times PC divided by PD. Okay. Now we have D on the variable side. Further, we say PC given D is proportional to PD given C times PC, and we don't care about PD. Why do we not care about PD? It's because PD is the input. We're interested in what class label an input has, right? So we don't worry about the probability of the input. We only worry about the probability of the class label, condition on the input. So we only care about PD given C and PC. Okay. PD will be the same for all different class labels. When we are given a piece of news, okay, we compare the probability of all class labels. D doesn't matter, because whatever PD is, we only need to choose one C that has the highest probability. Okay. That's why we can ignore PD. In the end, we have P, the last equation, PC given D is proportional to PD given C times PC, okay? Then we further simplify PD given C. Now, D is a set of words. We have the strongest independence assumption here. We assume that each word is independent from each other given a class label. So this again is the bag of word assumption, okay? Which means that the probability of D is the product of probability of every word in D. And we have the last term. So the product of every word I, the probability of Wi given C times PC. This is the naive Bayes model. This is a naive Bayes model. Okay. How many parameter types do we have? We have two types, PW given C and PC, right? How many parameter instances do we have? For PW given C, the number of instances equals to the vocabulary size times the number of class labels. For PC, the number of parameter instances equals the number of class labels. Okay, that's the whole model. It calculates the joint probability of D and C. Right. Now we parameterize the model, and every model parameter can be trained. How can we train it? Maximum likelihood estimation, right? Counting relative frequencies. Now, take PW given C. No, first take PC as an example. You're given a corpus, okay? It has a lot of news with labels. Now, the probability of one class label is the number of times it appears in your training data divided by the total number of documented training data, right? Relative frequency. This is intuitive. This is just like throwing a casino dice, right? So for your training data, you just count the number of class label C, okay? And then divide it by the total number of every class label. So that equals the number of documents. Okay. So that's how you estimate PC. How about PW given C? That's a conditional probability. So you should count the number of words in all the documents that are under the class label C, for example, sports news. When you calculate every word given sport, right? You just look at all the sports news and you calculate the relative frequencies of the word in those. That's PW given C. Okay, so given that we can train both parameter types, we can define the whole model. And you can actually train and classify. This is fun, right? I give you a set of news, and you go home and train your naive Bayes classifier. Don't forget smoothing, right? If you don't smooth your model, you get 0 power for all different stuff. Now you train your news given our data, and you download different news, form, technology, etc. And you feed the news to your naive Bayes classifier. You can see that it gives you the correct class label. Okay? All right. So this is for testing. For testing, you just calculate the probability of every possible class label. Okay, you select the most probable class. So next, so this is the generative story of naive Bayes model. You generate the class label and every word on the document by first generating the class label and then generating every word condition on the class label. So the generative story is like this. But this umbrella-shaped generative story is a little bit complicated before, right? You can simplify it by drawing a nested place notation figure. It's on the right. So you squeeze every word together and you use a box to box them and you write n. So basically you generate n words, okay, independently conditioned on C. It's something like this. So this is the generative story for the classifier. Okay, so here is maybe one last remark. Okay, two last remarks for today. So So one is how do you evaluate the accuracy of your classifier? Your naive-based classifier doesn't always give you the correct answer. So how can you know how accurate it is? You can do that by splitting your label data into a training set and a test set, right? You use the training set to train your model, and you calculate the proportion of your your test instances that are classified correctly. If out of 100 documents, 95 are classified correctly, the accuracy is 95%. Okay, so this is quite intuitive. This is how you evaluate. But of course, if you have hyperparameters, if you use add alpha smoothing, or if you use backhaul, you would better have a set of development data to adjust those values, right? So this is first thing. The second thing, and the last thing, last remark, I want to say, I want to tell you a feature. Okay? The parameters that we have for the whole today include words, right? Include n-grams, include word class pairs. These are called features. They represent characteristics of your problem. Let's take the word class pair as a feature. You know, given sports news, then the word shoot and go are more probable. But given science news, maybe shoot and go are less probable. Okay? So these probabilities, they tells you the association between words and classes that feature to represent your problem. Okay? So features, they can also overlap. For example, unigram and bigram features, they all describe the characteristics of words, but they overlap in the sense that their conditions are different. When we draw a generative story, okay, every word is generated only once. So in a generative model, you cannot have two different features to characterize the same word. Okay. In other words, you cannot generate the same words twice using different conditions. But these overlapping features can be useful. Okay. These overlapping features can be useful. Next week, we will delve into this kind of thing. We will start to parameterize model by taking a feature-centric approach. Okay. I leave some preview of chapter 3 to you, and that concludes this week. See you next week.